Okay, so I'm going to talk about a theorem about Bogomolov's about when a surface of general type actually has a big cotangent bundle. So first, let me just state this theorem. So theorem, and this is a theorem of Bogomolov. And this is in his holomorphic differentials paper, and it says fix the following. So S is going to be a surface of general type. And then we're going to take, we suppose that C1 of S squared minus C2 of S is positive. Then this implies that omega 1 of S is big. Okay, so I'm going to explain what these things mean. So let's recall that so this is a vector bundle of rank 2, and we need to talk about like positivity properties. So the general idea, and this is due to Hartshorn, there was kind of a zoo of positivity properties in the I think 70s that had to be cleared up. And they was that a positive, let's say E, a vector bundle, has positivity property P, and let's call this P, if and only if, and then this is the idea that, so that there's a line bundle, O of the projective bundle associated to E of 1 has property P. Okay, so for example, E is ample if and only if E, let's say O of P of E is of 1 is ample. Or let's say big, and this is big. Okay, so this is kind of the general setup. Let me remind you what big is for line bundles. So we say, so a definition. We'll say that line bundle L, L is big if so one of the equivalent conditions, so one, so these two things are equivalent, or so these two things will be equivalent. Okay, the first property says that the limit as t approaches infinity of let's do h0. So I'm going to take the global sections of some power of t, so x, let's say it lives on x, of L to the t, divided by t to the n is equal to a constant. Okay, so that it grows like t to the n, where n is the dimension of x. The other thing says that we can look at the associated embedding, the associated map to T. So there's so take L, and we look at the associated rational map of some power of it, and then this says that there's a rational map from here from X to some power of projective space, and it says that the image has dimension equal to the dimension of x. Okay, and then it'll be ample when this gives an embedding. Okay, so this gives an embedding. So this is what, and then so this is for here. This condition holds for t sufficiently divisible. Okay, so that's what we mean. Now I'm going to talk about the proof of the theorem. So the proof of the theorem, I'm going to kind of use two things that at the time of doing this, I'm kind of doing this because I'm going to have to give a talk on this in a second, or in a little bit. But the two things that are going to be a black box for me are that so we take x as surface. Then we need to show that the degree of a certain divisor looks like something. So then we take the projective bundle, which will be the projective bundle of omega 1 of x, and then we can take this to be the fundamental class of the projective bundle. And then the thing that I didn't know how to do was that this is going to be equal to c1 of x squared minus c2 of x. Okay, so this is the canonical class squared, and then this is going to be the topological, the Euler number here for the surface. Okay, the other thing that I didn't know how to do was that h0 of x times, let's do this bound, h2 of x in the symmetric bundle of R of omega of x, and this is equal to h2 of the projective bundle, and then you have O of the projective bundle of R. So this is how this thing works. The push forward of this is this. So and this is just comes from the definition of how this is built. This is equal to this, but that this is bounded by h0 of x of the symmetric power of omega of x. Okay, so these are two things that I'm going to assume. But let's assume these two things. So given A and B, so here's the idea. So we'll give a proof of Bogomolov given A and B. Okay, so this is the idea. So here we have that from the asymptotic Riemann-Roch formula we can look at this. So this is S of R of omega of x here, and this is equal to, so this is going to be the Euler polynomial. So but we have this projective bundle, and then we can look at the projective bundle, the rth twist of it. This is an inequality here, and then the asymptotic Riemann-Roch says, so this is from the asymptotic Riemann-Roch, says that this thing here is equal to, well, r cubed times the first chern class of O of P of P1, O of P1 cubed divided by 3 factorial plus something on the order of R. So this is a threefold since we did it with the surface. So this is going to be order of R squared. Okay, so there's something bounded by a constant. Okay, so this is the idea, and then we're going to relate this to our dimension. So okay, we have this. Okay, so now, so that's on one hand we have this, and then on the other hand we can write this guy. This is equal to h0 of, well, I'm just going to write it out, minus h1 of x SR omega plus h2 of x SR omega x. Okay, and this is clearly less than or equal to h0 of x of SR omega x plus h2 of x SR omega x. And then using the fact that we had this, so this part here, then we need to show the following, or we actually get the following. This is less than or equal to 2 times h0 of x SR omega x. And so combining these two things, we have that so we have a lower bound for this. So we have that O of R squared, okay, plus this R cubed C1 of O of P1 here over 3 factorial. So okay, if you're used to Landau O notation, this is like a terrible abuse of Landau O. But I'm just going to do it anyway. That this is less than or equal to, well, 2 H0 of x SR omega x. Okay, and so asymptotically, what we're going to have is that, that we're going to have this lower bound. So this is 6, so we have something like r cubed C1 OP over 12, less than or equal to. And this is what we want. Okay, so we have this plus this thing. Okay, and so this is the dominant thing. So this thing is going to tell us that this limit is going to exist, and so this proves the result. So yeah, from the definition of big, and the definition of big that we were using again was that, or the equivalent definition of big was that that this limit here existed. Okay, so so that being said, I'm gonna stop the video and thanks for watching.